Good morning, good afternoon, and good evening. This is the first session of the AFM Masterclass, which is held by Nanosurf in collaboration with Surface Car. Today, as I said, it's the first session, and we will bring to you a number of sessions till mid of next year. And with that, I would like to hand over to Dalia Blond from Surface Car to explain you a bit the purpose of the masterclass and also outline what you will see, what you will experience during this masterclass.
Thanks so much, Christian. Hello, everyone. We are very excited to bring this class to you. As Christian mentioned, it's basically a year-long course where we have a monthly webinar. You can see the outline of what will be covered every month. And the goal of this course is really practical. It's to help AFM users in their day-to-day imaging in terms of best practices, tips, common pitfalls. And we have highlighted the most common AFM modes that people use. You'll see we have here sessions on topography, on phase imaging, on electrical modes, force spectroscopy and associated calibrations. We'll also have a session on image processing. And so we really encourage you to tune in to the sessions that you need help on topics that you need help on, and ask questions. And of course, we're all available for questions on email afterwards. And we hope this will help you out in your day-to-day imaging. So enjoy and good luck.
So thank you, Dalia. It is my pleasure to start with the first session. One quick reminder before we start. Maybe you can post questions that you have during the session. Just in the GoToWebinar client, there is a section where you can post questions, and we can review these questions and answer some of these questions at the end of the session. So now let's start with session 1, why use AFM?
And that's actually a very good question. I hope that within this session, I can show you why AFM is a very powerful tool and what we can use it for. But first, let's start with a brief history of scanning probe microscopy. AFM belongs to the family of scanning probe microscopies, also known as SPM. This is a family of methods in which an image of a surface is generated by measuring an interaction between a physical probe and a surface by raster scanning that probe across the surface. Please note that other techniques that use raster scanning, for example confocal optical microscopy or electron microscopy, are not regarded as an SPM technique. The first SPM technique that was developed was scanning tunneling microscopy in 1982 by Gerd Binnig and Heinrich Rohrer. Both shared half of a Nobel Prize for Physics in 1986. So what's the working principle of STM? STM relies on tunneling of electrons between a very sharp, atomically sharp tip and a conducting surface. The resulting tunneling current is highly dependent on the distance between the tip and the surface. When scanning the sharp tip across a surface with only small height corrugations, we will see changes in the tunneling current. Feeding these current corrugations into a feedback loop allows us to maintain the current and, on the other hand, allows us to obtain topographic information on the sample. The resolution one can achieve this way is around 100 picometers, or even better. STM as such is a very flexible technique, so it's very flexible towards the environment, so no vacuum is needed. Let me show you two examples of the power of STM. The first example is adsorption of arachidic acid onto a graphite surface. We see here two images of these deformed arachidic acid monolayers, and we can see that we have submolecular resolution. From this image, but maybe better from the schemes below this image, we see that these images are mirror images, meaning that during adsorption we had a spontaneous separation of the enantiomers in the arachidic acid solution. The second example shows how STM can help to identify why doxorubicin can be loaded at different efficiencies to carbon nanotubes. Doxorubicin is a drug that is typically used for cancer treatment, and it is administered through carbon nanotubes into the body. As we can see from these two STM images, they are significantly different. Looking at the structures, researchers identified that in the left case, doxorubicin formed a helical structure with single doxorubicin molecules. In the second case, there's also a helical structure, but the doxorubicin forms dimers, and thus we can see a completely different arrangement of these molecules on the carbon nanotubes, and also a different density of doxorubicin on the carbon nanotubes. In 1986, the same year as the Nobel Prize was awarded for the STM, the atomic force microscope was invented. And only 4 years later, first commercial instruments of both AFM and STM were available. To understand how AFM works, let's have a look at the different components of an AFM. So the heart of the AFM is the AFM cantilever, which is a flat spring with typically a tip at its end. This tip is very sharp and interacts with the surface. Interactions between tip and surface cause a bending of the AFM cantilever. This bending can be read out using a laser focused on the back of the cantilever and reflected onto a photodetector. Changes in the interaction cause a change of the light spot position on the photodetector. The photodetector signal is transferred to the control unit, which uses a feedback controller to maintain the interaction between tip and sample constant. With the help of a high voltage amplifier, a Z scanner is used to adjust the height of the cantilever to maintain the tip and sample interaction constant. At the same time as the interaction is kept constant, the scanner is also used to translate the cantilever or the sample in X and Y direction to scan the cantilever over the sample surface. This way, an image is generated of the surface. The controller is interfaced with the PC to visualize the data and to allow control of the instrument, for example, to adjust imaging scans, imaging size, or imaging speed, or feedback parameters. Now that we know how AFM works, we can ask ourselves again the question, why use AFM? So the answer is AFM is a very versatile technique and the technique of choice for diverse applications. There is a number of techniques out there on the market that allow to characterize surfaces at the nanoscale, for example, SEM, TEM, TOF-SIMS, or instrumented nanoindentation. However, AFM has a lot of advantages over many of these techniques. For example, AFM is highly flexible. We can image any surface without the need of having, for example, a conductive surface. We can work in aqueous environments. That means we can work in physiologically relevant conditions. We have a very high resolution laterally and vertically. There's no need for staining the sample. Various modes allow us to get additional information on the sample, for example, mechanical or electrical information. And if done right, we can also handle very large samples. There's also a few drawbacks. One of them is that AFM is not the fastest technique. We don't have a chemical contrast. We typically have a small field of view. And we get surface properties, but not bulk properties. Let's quickly address some of the techniques I mentioned before. Electron microscopy, for example, provides a number of information based on the different electrons or X-rays that are emitted during shining an electron beam onto the sample. For example, one can get the morphology of a sample, here a polystyrene bead decorated with gold nanoparticles, or looking at different kind of electrons, the backscattered electrons, we can get a contrast based on the average atom number at a certain pixel. That means the gold atoms are heavier, have a higher atom number than, for example, carbon atoms from the polystyrene. In this way, we get a stronger contrast here for the gold atoms. To achieve real elemental contrast with an electron microscopy, we take advantage of the fact that upon shining an electron beam on the sample, we can also induce emission of X-rays using X-ray dispersive, energy dispersive X-ray analysis, which analyzes the X-rays emitted from a sample. And this way we can, based on the fingerprint of each element, can determine which elements are located in a certain spot. For example, here we have an iron matrix with some tin inclusions. Vibrational spectroscopy is typically used to identify molecules based on their chemical composition, meaning bond types that are in these molecules or functional groups. Raman spectroscopy, for example, relies on the inelastic light scattering effect and gives a fingerprint of certain vibrational states of the molecules. It is most sensitive to nonpolar bonds, so for example molecular backbones, and it can reach lateral resolutions of down to 0.5 micrometers when using a confocal setup. Infrared spectroscopy takes advantage of the absorption of infrared light to excite vibrational states from a ground level to an excited state. This is typically used for organic molecules and can also, depending on the way of the implementation of the technique, deliver resolutions between 0.5 and 10 micrometers. These two techniques provide complementary information. For example, bonds that have a strong Raman signal typically have a low infrared absorption and vice versa. Coming to some drawbacks of AFM that are a bit intrinsic to the AFM technology, meaning that we typically have a small field of view, which is around 100 micrometers and sometimes even more limited to 30 micrometers in XY. This means looking at large areas requires stitching multiple images. However, this is not an application that is typically AFM is typically not used for. Another limitation with the scanner is that the height of a scan that we can do is limited, typically something like 5 micrometers. Large range instruments can go up to 20 micrometers. And this requires that the samples are rather flat. So during the sample procedure within the field of view, one has to take care that one does not exceed these height limits. That means spin coating on flat substrates or microtome cutting are, for example, sample preparation techniques. Yeah, and last but not least, AFM is not a very fast technique. Typically it takes a few minutes to acquire a single image. For electron microscopies, it's typically just seconds. Nowadays there is faster techniques emerging, but these require typically ultra short cantilevers, and along with that also the systems have to have a small laser spot and a very fast detector readout and a fast controller. So after having looked at all these drawbacks or shortcomings of AFM, let's focus on what AFM really can do good, where it excels. For example, in its flexibility. I mentioned that there is a bunch of different modes that allow to detect different kinds of sample properties. The sample preparation, we saw that we need to be flat, we have to have flat samples, but apart from that, there is no tedious sample preparation. You don't have to stain the sample, dry your sample, coat your sample with metal, for example. AFM excels at measuring the true height, so there's no other technique that can provide the same height quality measurements at a similar lateral resolution. To measure morphology, AFM is very well suited due to also the capability of having the true height measurements. If it's just about morphology, SEM could be a competition, but however, there is no height information for SEM. Nanomechanical properties, we have a tip that we can use to touch the surface with. So we also have good ways to measure nanomechanics here. Nanoindenters can sometimes compete, but this typically depends on the kind of sample. For magnetic and electrical properties, AFM is unbeaten, so there's no other technique that can provide these properties at a similar resolution, lateral resolution. And in situ imaging, something which, for example, is needed for biological samples where we need to be in a liquid environment in order to keep the sample in a proper state, proper hydration state. And AFM is the technique to go for in situ measurements. Other techniques, for example, SEM, don't allow to measure in an in situ environment. Last but not least, there's nanomanipulation. I will show you in the end that we have a bunch of different techniques and possibilities to modify our samples in situ in various ways. So talking about flexibility, here is a kind of a small collection of AFM modes that an AFM can do. They're grouped by mechanical, electrical modes, magnetic modes, some optical modes, and also other lithography modes like lithography or 3D nanoprinting or thermal microscopy. All these modes can be used to do measurements on different kinds of samples, and ultimately what one does is one gets certain surface parameters. For example, the surface roughness, which is still the most important parameter, surface parameter, for example, for industrial applications. Layer thickness. Recently, a lot becoming very popular is measurements of stiffness, elasticity, or adhesion, doing nanomechanics. But we can also address the work function, or for example, electrostatic forces on samples. Before we can measure a sample with one of the modes mentioned before, we have to make sure that the sample is prepared in a correct way. So the advantage of AFM is that there is not a lot of sample preparation that needs to be done typically. So we don't have to put samples in vacuum, we don't have to stain or coat them. We can even work in liquid environments. With tip scanning AFMs, we can also handle very large samples if we have a proper stage to allow this. And we can integrate tip scanning AFMs easily into optical microscopes, which allows us to do simultaneous optical and AFM investigation on such samples. Yeah, and last but not least, we should not forget, we're looking at things at the nanoscale. So, albeit there's not a lot that we have to do, one thing that we have to take care of is that everything is clean. Because if something is not clean, we will easily see that at the resolution that we can achieve with the AFM. In the previous slides, I've been talking about AFM being a high resolution technique. So what does high resolution mean in that sense? For example, the vertical resolution. The example here shows an AFM topography of a strontium titanate crystal, and we see that there is layers in this crystal, and the height difference between these layers is a unit cell of the crystal, which corresponds to 4 angstrom height difference. We also see that there is substructure on top of each of these layers. We can now calculate a height histogram of this image, and we see that there is a number of peaks, and each peak corresponds to one of these layers as they are separated by 0.4 nanometers from each other. Also seeing that we can nicely separate these peaks, we can clearly state that the resolution that we get is well below 0.1 nanometer in this case. But what about the lateral resolution? So the answer for the lateral resolution is, yeah, it really depends. So the lateral resolution depends on a few factors. If we model the tip as a sphere and the sample also as a sphere or a half sphere, and we bring these two into contact like we do when imaging, we see that we create a contact area here. And the diameter of this contact area limits the resolution. So this contact area here, or the contact radius A, depends on the force that we apply to the cantilever, the elastic modulus of the sample surface, and of course on the radius of the tip. As an example, when using a given force of 1 nanonewton and a tip radius of 10 nanometers, we can achieve a resolution of around 1 nanometer on a silicon surface and around a resolution of around 10 nanometers on a much softer rubby polymer surface. This shows us that ultimately to get the highest resolution, we have to try to image the sample at the lowest possible force. With this and the following slides, I would like to show you some examples of where AFM really excels and outperforms other techniques. For example, here we see a morphology. This is a SEM micrograph. We can nicely see the cell on this collagen sponge. However, on a AFM image, we can also nicely see protrusions of the cell. In this case, it's grown on a glass petri dish. The advantage of the AFM is this was done in situ. Basically, we were imaging in a liquid environment in cell culture medium, and we did not have to dry this sample like for SEM. And we have a real height, a true height information out of this image. The true height is also something that only AFM can measure well, as said before. For example, it can be applied to measuring these gratings where we have trenches of about 390 meter depth and approximately similar width. And depending on the cantilever, one can measure trenches even with higher trenches or deeper trenches or with a higher aspect ratio. But one can also measure flat samples and get accurate information on the height, for example, on these multi-layer graphene to allow determination of the number of graphene layers. So this shows that AFM can measure over several orders of magnitude the height very accurately. So now coming from topographic measurements to nanomechanical properties, since we have the tip that we can bring into physical contact with a sample, the AFM is a great tool to measure nanomechanical properties of samples. There's a bunch of different parameters that one can address this way, for example, the friction force, and very popular nowadays, stiffness, elastic modulus, and adhesion or unbinding forces. There's a number of related techniques or modes, that are used to measure these parameters, for example, lateral force imaging, phase imaging, microbiology, or the most popular one for spectroscopy. So now let's have a quick look at the difference between an instrumented nano-indenter and AFM for measuring nanomechanical properties. In AFM, we have this rather soft cantilever with its very sharp tip that we bring in contact with the surface. We gently deform the surface in the elastic regime, and this way we get elastic properties of the surface. And after retracting the cantilever, the surface goes back to its original state and is basically not destructed, not harmed. In contrast, a instrumented nano-indenter has a stylus that it brings into hard contact with the surface, and basically plastically deforms the surface. So after retracting the stylus, we have an indent in the surface, meaning the surface is basically destroyed. This also means we cannot get a very high resolution because this hole is rather big, because the indenter tip is rather big. On the other hand, the AFM tip is rather small. That means we can have a high vertical and lateral resolution in our force measurements. Having a softer spring on the cantilever also means that we have that we effectively measure better on softer materials, although there is also very stiff cantilevers that can measure on very hard materials and allow also plastic deformation. However, the AFM is not optimized for very hard samples as the nano-indenter would be, which excels really at very, very hard samples. Let me show you an example of how we can combine high resolution imaging, for example, of these virus capsids on the surface here, with nano-indentation. So first we identify the location of these virus capsids, and then we bring the AFM cantilever on top of these virus capsids and approach the cantilever towards the surface. So we start far away from the surface and approach the tip towards the capsid. At some point we start touching the capsid and we apply a force to the capsid. We see here a more or less linear response, so basically the stiffness or spring constant of this capsid. At some point we see a drop in force, and we see this peak here, and this is the position at which, or the force at which we penetrate the capsid surface. Basically break the capsid open. The force drops and we continue approaching the cantilever towards the surface, and at some point we touch the lower surface of the capsid from the inner side of the capsid. We again apply a force. At some point we see a plateau. This is when we break through this protein layer and finally touch the glass. So with this kind of measurement we can get not only the breakthrough force or the stiffness of the capsid, we can also measure the height of the capsid at the position where we indent, basically the difference between the initial contact and the glass surface, and also the thickness of the membrane layer, which is the initial contact with the lower membrane or protein membrane and the glass surface. After the indentation measurement, we can re-image the sample and we see that all these virus capsids have a small black dot. If we zoom in further, we can see that there is a nice indent within this virus capsid, but also here. And we can see that surrounding this indent, the structure of the capsid is more or less intact. So while with the virus capsid we were typically in principle addressing a single point on the surface, we can now also measure or map the properties of an area on the surface. Here we took an AFM image initially, and then we selected a certain area of this AFM image in which we perform 256 by 256 force curves, so an area of force curves which provides us with a very high resolution map of the mechanical properties. For example, the surface here is a polymer film with some metal layer on top. So what we see is that the adhesion on the polymer film is higher than on the metal layer. We also see, for example, for the modulus, that we have a lower modulus compared to on top of the metal surfaces. And there's also something that's called the snap-in force, but I don't go into detail here, but we also see that there is some contrast on the snap-in forces, meaning there's also some material property that we can attribute to the snap-in force here. So using this approach, we can directly correlate the topography with the mechanical properties of the sample. Now switching from mechanical measurements to electrical measurements, one can think of the simplest measurement one can do is to measure a current between the tip and the surface, as like we do in STM. To do that, we need a conductive AFM cantilever, and then we can image across the surface while applying a bias voltage to the tip. And what we then can measure at the same time as topography is a current through the tip. And for example, here we have a sample with different transistor contacts, and some of them do not show any conductance at all, no current at all. Others show a small current, slightly elevated current, and a high current. And so this way we can identify different structures within this chip assembly. Gain a little bit more insight onto the electric properties of these contacts. We can, for example, address 3 different contacts marked with the blue, red, and orange arrowheads in the conductive map, corresponding locations on the topography map. And we can do an IV curve on these positions, which means that we apply or ramp a bias voltage while we push the cantilever onto these locations and measure the current that is flowing through the cantilever at these positions. We can see that, for example, the black curve has no current at all, and the orange and the red curve have significantly different current voltage profiles. Another electrical mode, which is a bit more sophisticated than conductive AFM, is KPFM, Kelvin probe force microscopy. And this mode allows us to determine the contact potential or the work function of a sample. We can do this measurement on, for example, such a stainless steel surface, and here we see hardly any contrast on the topography image. However, in the KPFM image, we nicely see that there's different domains. We have different surface contact potentials in the steel here. So meaning we have different domains, materials with different properties. If we do these KPFM measurements, for example, with a magnetic tip, these are typically also conductive and can thus be used for KPFM measurements. We can combine these KPFM measurements and topography measurements with MFM measurements. And this way we create another layer of information for the sample. From the MFM measurements, we get that some of the domains, basically everything that is blue in the KPFM channel, has basically no magnetic contrast. And everything that's green in the KPFM channel has some magnetic contrast. Some domains have a light magnetic contrast here and here, but for example, the domain in the center over here has very strong magnetic contrast. We see these striated patterns, domains, and this alternation between dark and bright indicates that here we have domains of different polarization, magnetic polarization, alternating. Now we leave the electrical measurements and come to in-situ imaging. In-situ for AFM mostly means that we are measuring in a liquid environment, for example, for electrochemical experiments, but as the examples here will show, also for working with biological material, in which we need to have the material properly hydrated to keep it alive in the case of cells, or to keep it functional and keep its proper structure, as in the case of some other examples I will show on this slide. So what we see here is the cells that I've shown before. They were acquired in cell culture media, it's live HeLa cells, and we can combine it with optical imaging, and we see down here these 2 cells that we see also here in the AFM image. Then we can go a scale smaller, length scale smaller. We can image virus capsids adsorbed to an intact nucleus. This is a 5 micrometer big soft nucleus to which these capsids are adsorbed, and we can nicely resolve the structure of the capsids adsorbed to this nucleus. Another order of magnitude smaller, we can look at, for example, DNA. Here we see a bunch of DNA molecules. They are crossing over here, for example. But what we can also nicely see is that there is some banding structure on these molecules. So there's some stripe pattern. If we create a height profile from a part of this DNA, we get this pattern shown here in the inset, and we see there's some periodicity to it. If we measure the periodicity between every second valley, for example, we see that this corresponds to 3.4 nanometers, which is exactly the pitch of a helical turn in a DNA molecule, a double-stranded DNA molecule. And this means that we basically see here with this stripe pattern, this banding pattern, the major and minor grooves of DNA. So the last example shows you that we cannot only image static things, we can also look at dynamic processes, like here the assembly of DNA tripods into this hexagonal lattice. This has to be in liquid, otherwise this hexagonal tripod DNA could not diffuse around, could not bind or desorb from the surface. Having an AFM with the possibility of moving the cantilever around in 3 dimensions and having the possibility of different cantilevers, one can think also of nano manipulation. For example, here we deposited charges in the shape of a Swiss cross on a surface and afterwards imaged these charges with Kelvin probe force microscopy. But one could also, for example, locally scratch or indent the surface or do thermal modification of a material. This example down here shows you how we created a nano or micrometer sized QR code by using a heated cantilever tip, slowly melting or gently melting part of the polymer surface and pulling out small nanorods. And the last example I would like to show you uses fluidic probes, fluid FM probes with a hollow cantilever, which can be used to, for example, in this case, deposit material, fluorescent dye, into a single cell. And we can see that the dye was deposited only in this cell and not into the neighboring cells. We can very locally deposit material or extract material on surfaces or into, for example, cells. So I'm slowly coming to an end with the session. One thing that I would like to mention here is the fact that AFM can also be used to access large samples. Many AFMs are just built to accommodate very small samples, a few tens of millimeters across and in height, but there are systems out there that can also address large samples. For example, this one, which can handle 300 millimeter diameter samples up to 45 kilograms of weight. But there's also other stages that can be built for even larger samples, in this case 500 millimeter diameter, or even larger ones were built with diameters of 1500 millimeters. And these stages are only possible when having a tip scanning AFM. So with a sample scanner, the performance of the scanner, which would then be below the sample, would decrease significantly with the weight that is loaded on top of these samples. So why am I telling that? So these AFMs are typically not that much used for research, but for industrial applications, such AFMs are of great importance. I hope with the examples that I presented during this session, I could show you for which applications AFM is the perfect tool to characterize your samples. AFM provides high spatial resolution, provides the true height of samples, and can measure the nanomechanical and nanoelectrical properties of these samples. The sample preparation has only a few requirements with regard to sample roughness, but otherwise does not require any special treatment like drying, staining, or coating. Moreover, this is a very important fact, if done correctly, AFM is a non-destructive method, which you cannot say of many of the other methods. So that leaves me just with an announcement for the next session. The next session will be held by my colleague Eugene on October 20th. We would be happy if you tune in again. And he will talk about the best practice for topographic imaging. And in this following and the sessions following after that, we will go into more detail and explain the modes that we presented here, for example, and the applications that we presented here. And also give you some hints to watch out for things that you have to be aware of when doing your own measurements. During the registration phase for this masterclass, we received quite a number of requests if we could provide certificates for attending the masterclass. We decided that we will hold quizzes after each session that allows us to kind of test you if you want to have a certificate. We will provide an email with a link to the quiz and also to the session for on-demand access in around 2 weeks. So this way you will have a bit time to think about what you've heard. You could also watch the session again, and this would help you to then answer the quiz. The quiz would take typically only 5 to 10 minutes to complete, but please make sure that you use the email address that you used to register for the masterclass also for the quiz. Otherwise, we cannot link the quiz to you towards your registration. So finally, I have to thank you for your attendance. I hope you tune in again. And we will now answer some of the questions that came in during the presentation.